Welcome everyone to this paper club. Today's presenter is going to be Christina. Christina is a regular attendee of paper club. So this just goes to show that anyone can present at paper club, and we actually encourage it. So please feel free to present yourselves. Christina is going to be speaking about an iteration of UNet, which was a paper that we discussed a few weeks ago. And so this unit was for segmenting images, particularly in the medical domain when there is not much data. And then probabilistic unit is a very interesting addition to this architecture. So Christina, please go ahead.
Hello everyone, my name is Christina, and today I'm going to present the probabilistic UNet for segmentation of ambiguous images. The paper has been released first in 2018, and there was a revision in 2019. So I'm going to talk about the latter. Right, so what are they trying to do in this paper? They try to learn, again, the setup is the segmentation here, but instead of predicting one possible segmentation, they want to predict multiple and different variations of those. So they want to learn a distribution of segmentations given an input on a class of images which are ambiguous. So the context alone is not enough to resolve by ambiguities, and even for the ground truth, there are multiple truths. So this is very common case in the medical imaging. So sometimes radiologists may go through a CT scan and would even disagree on the presence of anomalous region and moreover if there is a cancer or not. So this is what they primarily target the application of this approach, but not only. And then they devise a set of experiments that show the performance of the model. All right, so the problem setup. Usually segmentation methods are aiming to predict pixel-wise probabilities, whereas when there is no covariance between the pixels. Whereas here there is some ambiguity, and then we have the covariance between the pixels. The traditional methods would provide us the most likely hypothesis, which is usually one or many of the same, and this might lead to misdiagnosis, especially in the case where there are very rarely occurring conditions, and so this would lead to suboptimal treatment. What they want here is, in case of this ambiguity, they want to have multiple hypotheses saying that this is a probable version, this is a probable version, this is a probable version of the segmentation map, and then in the medical setup, go ahead and do more tests for the patient. Maybe better treatment, they can arrive for better treatment with, that's what they hope. All right, so how, 2 weeks ago, let me go back. 2 weeks ago or 3 weeks ago, there was a discussion about the UNet paper on the NPlan Club. So I'm not going to go through much in detail about that one. So basically but in that setup, we are trying to learn a segmentation using an encoder-decoder structure with the skipped connections, which has a shape of U if they put it graphically together, and that's why that is called the UNet. There is no probabilistic component, and the latent space, basically we just have a vector where the information is encoded. Now I want to bring the conditional variational autoencoder into picture, because that is another component that the authors of this paper are using. So this is a probabilistic setup for generating data, where we are trying to learn the log likelihood of the data, maximize the log likelihood of the data, and basically find that what's a generating model behind it. The setup is that we have the encoder and the decoder network, and the encoder provides a distribution of the latent space encoding from which we are sampling and then going to decode, pushing it through the decoder. In the conditional variant, we are also conditioning on something. In the original paper for conditional variation autoencoder, it was on the class. So basically for MNIST, the VAE itself doesn't know that 3 is a 3, and so if you wanted to produce a 3, it's just going to produce some number. If you're using the conditional version of it, you will tell it that, yeah, give me a 3, and then it will give you a 3. Or a given other class. So that is our loss in the CVAE case. Now let's see how the authors actually try to solve this task that they set for themselves. In this slide, I'm just going to talk about high level, and then we are going to go in depth a little bit later. So here they are combining the two. They are combining the UNet together with the conditional variational autoencoder piece. And so here they are presenting two architectures. One is for the sampling process of inference, where we feed the image, which goes through the prior net that provides us the parameters for the normal axis-aligned Gaussian, from which we sample an embedding. And each of these points in this latent space corresponds to a variant of a segmentation. Now, the same input image goes through a UNet. The UNet learns feature representations and the regional information about in those feature maps. And then later, at the output of the UNet, they are broadcasting the sample from the latent space, and then that goes through the final part, a 3 1-by-1 convolutional neural network, and that produces a segmentation. In the training setup, we've got the prior net and the posterior net, which we're trying to bring closer together via the KL divergence. And then we've got the cross entropy part of the loss, where the predictions, we're trying to get the predicted segmentations to be as close to the ground truth. I'm going to go through this more in detail a little bit later, but let's see how actually others are doing the same task. So one option is that they talk about is the dropout UNet, when they are introducing the probabilistic component to the UNet by adding the dropout. And this actually does give the probability distribution for the pixel-wise uncertainty, but it gives inconsistent outputs. Another option is to go for ensemble of UNets trained separately. It does produce consistent outputs, but those are not diverse. Well, we train them separately. They are all giving the most likely outcome. So then, yeah, we have very similar outputs. And they are not able to learn rare variants, only the most likely, as it's only the most likely hypothesis. And actually, well, you need to fix the number of hypotheses at training. So that would be the number of UNets in the ensemble. And if you want to produce many variants, you will need that many networks. So not very convenient. Then there is another variation of the ensemble, which is you don't train it separately, but jointly. So with each of the UNets being ahead in the network, and then they are connected together at the very end. So this, since it is able to, this network is trained jointly, it is able to capture a diverse set of variants. Now we are not only in the mode of going for the most likely hypothesis, but it doesn't capture the occurrence of individual variants. And also, again, you need to predefine the number of the hypothesis. So it doesn't scale too well to large number. Then they mention a little bit about the graphical models, which capture diverse set of variants, but are only confined to structural problems with tractable graphical models, and more interesting distributions can't really be tackled with these approaches. Then in the paper, they go to explore what is the other work in the image-to-image translation domain that they can borrow from. And they mention about the GANs, the generative adversarial networks that are using the that are rooted in the game theory, where they have the generator and the discriminator that are beating against each other to, in the end, produce the most likely outcome that can fool the most likely images that can fool the discriminator, whether these are real or not. Right, but these suffer from, the traditional version suffers from the mode collapse. So it produces most likely one image or very similar images and not the diverse ones. Now this has been solved in the bicycle GAN, which is using the conditional variational autoencoder GAN together with the conditional latent regressor GAN. And they're combining the two, constricting them and adding a little bit more components to the architecture and the loss. They fix the prior distribution, and posterior is only conditioned on the output, unlike in the case of this paper. But that is, and they actually, this is the one of the baselines that they're going to use later, which they refer to as image to image a network. Then they're talking about another method that does use very, very similar approach of variational autoencoder together with UNet for generating appearances given a shape encoding. So basically, as if they have a sketch of a bag or a shoe, and then they want to produce the realistic images of those bags or shoes, and as many as we can imagine. Since it is very, very similar approach, they try to differentiate themselves a little bit. I brought up the picture from that paper just to say that actually there are some differences, because as we see, the sampled latent representation is the encoding is being added to the middle of the UNet instead of the beginning or at the end, and then there is no conditioning on the input. And then they mention another model, the probabilistic model for structured outputs, as they refer to it. And from here, they are borrowing the idea for the similarity coefficient, which is in this case, so the similarity coefficient between the ground truth and the predicted distributions. There it is being used as a loss, and here they use it as a matrix, but the idea for this distance is quite similar. All right, so let's, they mentioned that their major contributions are that they provide the consistent segmentation maps, and for pixel-wise probabilities, and it is quite successful, and the results are showing that they are able to learn well the joint likelihood of the model, which is what the variational autoencoders are trying to do. They can scale to arbitrarily complex output distributions with very rare modes, and also they claim that the calibrated probabilities for segmentation, they provide the calibrated probabilities for segmentation modes because they're able to capture the frequencies of the modes. They talk about the computationally cheap sampling because they add to the sampled encoding to the very end of the UNet, and then it is just a couple of convolutional layers. And then they are talking about the assessment of performance quantitatively and not just qualitatively. All right, so let's look at a little bit more formal representation for the figure 1, which was about the sampling and inference. Here we have the random sample from the prior that is being conditioned on the input image, which is an axis-aligned Gaussian with the mean conditioned on x on the image and the weights w, and a diagonal variance conditioned on x and w. So what Gaussian axis-aligned Gaussian means in this case is that the variance covariance matrix has zeros everywhere else apart from the diagonal, but diagonal has different values. So basically there's the vector. Okay, and so they use this conditioning on the image to enable to capture variant frequencies by allowing the corresponding probability mass to the respective latent space regions. So once we have the sample, this random sample encoding, we get it through the combination function, which is the 3 consecutive layers, where it's of 1-by-1 convolutions, which is where we feed the feature representations from the UNet with input x and the parameters theta, our random sample, and is conditional on the weights psi. And this is our segmentation map.
May I ask a quick question?
Yes.
The sigma priors, are they learned variables?
Yes, they are being learned.
Okay.
Yes. So they train both the prior and the posterior.
So
they are not fixed.
Yeah. So the mean and the variances are the output of the prior network, right? So
yes,
they are
yes.
machine learning outputs.
Yes.
I actually had a bit of a doubt that came. I don't know if maybe you have a better intuition, because they don't explain it in the paper, which is why do they choose to parameterize a Gaussian distribution, and in particularly an axis-aligned Gaussian distribution, and not something different? Do you have an idea?
I don't, and they don't say anything about it. One of my criticism for the paper is going to be that they only present what they do, and there is very, very little on why they do certain choices. And even if you go through some of the papers, skim through the papers that they're linking, you can try to get that evidence of how others did it and why they did it, but they say nothing in this paper. Paper, so we can only speculate.
I can see that, because in variational autoencoders, it's very common to use the prior network to parameterize a Gaussian, but they're typically very general, and since they make the whole discussion about the medical sector, I was wondering if maybe maybe they could try a particular type of distribution or parameterize something different to generate, let's say, more guided guesses about how the latent space should look like.
Nope. This is what they're doing.
Yeah.
And they're not really explaining too much why.
Yeah.
Maybe there will be some more ideas during the discussion.
Yeah.
Okay. So basically, this is again the figure 1, picture A, for the sampling for inference. So what we are doing is that feed the image. there we have it goes through the prior net, we get the latent space encoding, and then sample from it m times n encoding, vector z, and we add it to the output of to the last feature map of the UNet, and feed it through this 3 1x1 convolutional mini network, and then we get the output. Then what is one of the selling points of this choice is that they don't need to retrain this prior net and UNet many times. They can just use the outputs and sample as many variant encodings as they want, and then it's computationally quite cheap to just go through this last leg of the architecture, and then we sample in this picture the second vector, we get the second segmentation, and we sample the third one, we get the third one, and then so on and so forth. In the paper, they refer that they do it 6 times, but the dimension of this latent vectors then later has been defined identified in the process of the training, which one works better for which use case. Okay, now this is the part of the training, the formal explanation. So this is the figure to the figure 1b. There we have a random sample from the posterior queue that is both conditioned on the ground truth segmentation mask and the input image. What is interesting about this posterior is that we are predicting multiple outputs. And this is also an axis-aligned Gaussian, but the mean and the variance are then parameterized by the input image, the segmentation mask, and the weights nu. Then combining the previous steps, we get the predicting segmentations ideally identical to the ground truth. And the training procedure, we try to optimize, to minimize the loss, which is negative elbow. So we are maximizing the elbow in this case, the variational lower bound. And there we have the 2 components, the cross entropy loss between the produced segmentation and the ground truth segmentation. This PC is the pixel-wise categorical distribution, and the S is basically is the segmentation, which serves as a parameterization of this pixel-wise conditional distribution. Then we've got the callback with the KL divergence, where we try to bring the posterior and prior closer together, and they borrow the idea for the weight vector from things beta VAE, where they have an additional weight factor. This is how it looks on the picture. So there is the prior net and the posterior net, which we try to bring the 2 latent space, the 2 distributions closer together with the KL and the cross entropy part of the loss, which is applied to predicted segmentation and the ground truth. All right, so let's go to see how well this method perform. They use this generalized energy distance to compare the distribution of segmentations. Basically, as a basis of it, they use the distance as 1 minus intersection over union. And they use this over instead of dice because it does satisfy the requirements for a distance, for an actual distance metric. So here we've got the double expectation of distance between the disagreement we have between the ground truth and the predicted sample, minus the disagreement between a pair of predicted masks and the disagreement between a pair of the ground truth masks. And there can be different number of the predicted masks in the case. So the first use case that they're applying it to is the medical imaging segmentation for lung abnormalities, and there they have 4. They have 4 predicted ground truths, 4 ground truth segmentation, and then they have arbitrary number of the predicted segmentations. All right. So the baseline. Yes.
Sorry. For the method to work, is it necessary to have more than one ground truth per image?
I don't think so.
No, not necessarily. They also, it's not necessary to have the one ground truth.
So if I may add that this doesn't fall into part of the training, right? This is part of the more assessment.
This is metric. This is metric. Yeah. This is not loss.
So this is, I don't know, this is something that you see a lot in the medical sector, because ground truths, there is no real ground truth, especially when segmenting images, because different experts can have different segmentation. So what they're trying to do here is to account for that, let's call it natural error in the ground truths, which is that first disagreement between, that second disagreement between ground truth masks. And then for what I interpret, they're just trying to say, well, let's say that my model also models a disagreement. So when I sample different values, I'm also sampling like different opinions, different expert opinions.
Yeah, it's just because it seems that the one of the key features is that you have these multimodal predictions, and I wonder whether that only happens because you also train on a multimodal set, or whether that is a natural occurrence if you have just many samples.
So basically, here you can, so multimodal predictions, you can sample as many as you want, and then you can keep comparing it to one ground truth.
Sure.
But you're not going to get as many variants of this one, I suppose, if you only have one ground truth.
Yeah.
Because just the model won't be able to learn those.
Yeah.
I mean, it will have some variations, but being conditioned on the input image constraints this latent space.
Yeah.
Yeah, and it does, like, the architecture is very oriented to these kinds of problems where there is not a single ground truth, right?
Yes.
So it's not like, I don't know, a couple of weeks back we showed some of the data sets that are used for these kinds of problems, or the more general kinds, and it's like segment the pineapple or the dog or the airplane, so it is a single ground truth. Whereas show me the segmentation of a tumor is not necessary. There's not necessarily a single ground truth.
Yeah, so the very ground truth for a tumor would be autopsy, or in the worst case scenario. But then also I don't think somebody's segmenting those, or if they or the surgery. But again, I don't think that, I haven't seen data sets that have everything segmented with the real ground truth.
It could be just quite expensive, right? Getting such a data set where you possibly have multiple ground truths for each sample.
Yes, well, surgeries do happen, and sometimes people die as well from cancer. But it's not that people go back to the images, medical images that have been taken, and they segmenting every pixel based on what they get in the end. So the real ground truth is out of scope, and then different people can disagree on pixel by pixel.
Yeah.
Especially on very anomalous regions or very complicated, very complicated organs.
Yeah. Also, one thing that they point out, which I find very interesting, that they took into account, is that sometimes experts can disagree on whether the thing that's showing on the image is actually a tumor, for example. So they also allowed the model to predict that there is no, like, there's nothing to segment, which is interesting.
Yes. So for the comparison, they use these 4 models as a baseline. So the aforementioned dropout UNet. So everywhere on the pictures, we have the arrows is a flow of operations, blue blocks, the feature maps, red blocks. Here is the dropout units. And then the green blocks are the broadcasted latents. And well, they have it on the image-to-image VAE. But over there, this sample, so this is the bicycle GAN, but the sample, the embedding sample from the latent space, is being appended at the beginning of the unit, not at the end. And then, of course, they modify it a little bit to fit the this particular task, and not the generator. Not generating full images, only just two masks, which is, this is a supervised setup. Then we've got the M-heads, the UNet ensemble, the ones that we spoke about earlier. All right, so they test their method on 2 data sets. One is the lung abnormality segmentation data set. As I remember, they collaborate with the Medical Institute in Germany, where they got the data set. And the other one is the Cityscapes data set. So over here, the setup, we've got the 1018 lung CT scans from 1010 lung patients. They had 4 radiologists producing 4, so each producing an annotation mask. And they had, from a total pool of the radiologists was 12. And then 4 of them were randomly selected to, or maybe not randomly, they don't really specify there. But the radiologists, so they were independently giving their opinion, what should be the masks, and then they had the chance to see what others said and then correct themselves. So then they resampled the CT scans and they cropped the 2D images to just concentrate on the part that has the ambiguity in it, and just take away the pieces where the model agrees. Everybody agrees that there is nothing, and the models agree that there is nothing. So in the end, we have 180 by 100 by 80 pixels centered at the lesion positions. Then they apply augmentations to this, and in the end, we get we get the training set for 722 patients with almost 9,000 images. The validation set is 144 patients with almost 2,000 images, and the test set is the same numbers. They make this condition that 3 masks per image can be empty, as experts can disagree. All right. So coming back to the metric that they have used to assess the results quantitatively. In this case, we don't know the true ground truth, the distributions. We have samples from it. So this is the version of the of this metric for this use case. here we can see this metric, the realization of this metric is a function from the number of samples. So they sampled one time four embeddings, 8 and 6 and 16. And well, they are showing that while in the case of one sample, their model, the green triangle, is not performing the best, it's kind of second best, and the unit ensemble beats it. Everywhere else, their model performs the best, but they are very close to each other. So they perform the best still by a thin margin. Though in the case, then they reporting that in the case of 16 samples, they are, I mean, this difference is actually significant with a quite low p-value. But still the difference is not too large. And then we can actually see this visually. We have the actual image, the CT scan, and then what the 4 graders thought about it. And this is what Carlos mentioned, that one of the radiologists thought that there is no anomaly, there is no lesion. And the other 3 thought that there is. And we can see how each of the methods performed. You can see that the dropout unit provides some sort of very similar to each other images. They're all very hazy. Then the unit ensemble, as expected, is providing the most likely outcome, and they are all very, very similar. And the M heads, they vary a little bit more, but still quite the same. And then they don't have rare modes where there is no lesion. And basically the last 2 are performing the best if you look visually. And then as we can see that the probabilistic unit actually produces different variants that look differently and also have some cases where there is no segmentation. Any questions? Anything with regards to the first setup, the first test?
If I can just make a small comment, which is that one of the things I really liked about this paper is that they prefer to go for the augmentation path rather than automation, right? I think that they got that pretty spot on, in that clinicians will typically not look for something that will tell them where the lesion is, but they will look for second opinions, so to speak. So this is basically giving them, well, here you have 6 different opinions, and now you make a decision on what needs to be done. And those opinions may also be, there's actually nothing to see here. So I thought that was a really interesting approach from their side.
I thought so as well. Thank you for the comment. All right, let me proceed. Then they present the second use case where they have everything controlled. And they use the Cityscapes semantic segmentation, which gives the images of street scenes taken from a car. And then they have the annotation for like semantically segmented components that are there, like the road, street, the pavement, and so on and so forth. So altogether, there are 19 classes, and they artificially create the ambiguities by randomly they are choosing 5 classes and then randomly flipping the labels to newly introduced classes with different probability. So they flip the sidewalk to sidewalk 2, the person to person 2, car to car 2, vegetation to vegetation 2, and road to road 2. So this is going to create ambiguity in the image, even though there is the same tree segmented out, but sometimes it is vegetation, sometimes it is vegetation too. And then in the end, they have the 35 discrete modes with probabilities ranging from 10.9% all unflipped down to 0.5 flipped. They have a training set of almost 3,000 images. The test set from the Cityscapes contains 500 images. This is the official test set, and then they take out 574 images from it for their internal validation set. So basically, they just take 3 cities. These are not randomly chosen images. This is specifically 3 cities. There are a little bit of the differences in this case because into the metric, because they have access to the full distribution that they have defined, and this is the direct delta distribution used directly in the estimator. And again, we have the number of samples 1, 4, 8, and 16. And they are adding additional weight component everywhere where there is the ground truth image involved. And again, the method is not performing as well in the case of the one sample. Again, the UNet in sample is doing the best. But in the subsequent number cases where the number of samples is higher, they are consistently performing better, outperforming the other baselines. And here the difference is a tiny bit, is more. And this is also confirmed by the p-value of the test. Yep. So this is how we can see it visually. The ground truth image, and then the ground truth modes for this image with some flipping. So here we see everywhere with the purple, that is the that would be the road, and this would be road 2, the green one, so that is flipped. And then we can see it on the pedestrians, or that the trees are flipped, and so on and so forth. And we can see that dropout UNet again produces very hazy images. There's a lot of noise, and they are just taking most likely classes, so the original ones. Again, the UNet ensemble, we don't see the differences in colors. So the road is always road, no road 2. And the MHATs basically has a very similar case for the road, but for the vegetation, for the pedestrians in these images, we can see that sometimes they get the more rare modes. The image-to-image VAE and the probabilistic UNet are performing the best over here when you look at it visually. Now, given that they have full information about the distribution in the setup of the Cityscapes experiment, they are also able to see, to support a little bit more the calibration, the well-calibrated model claim. So they are comparing the frequencies of the distributions for the ground truth on the x-axis and the predicted one on the y-axis. And we can see that the dropout UNet ensemble, and MHATs, they are falling for more the more likely case. The MHATs is doing a little bit better, but they are not getting the frequencies at all. The image-to-image VAE is the best from the baselines, that is able to capture different modes, but is not getting the frequencies right. And their method is getting the frequencies the best, because all are along this line. So the predicted and the ground truths are very, very close together. In the appendix, they have an additional support to this claim. Here they are showing the they have the pixel-wise frequency estimation, so how often the class pixel has been assigned to the correct class, and this is the mode-wise, what we see vertically, and the white box is the ground truth, and the green box is the estimated frequencies. We can see that these are very, very close together, and if you look into the appendix over there, you can see that all the others are very far off this kind of performance. There is one more thing that they do in this paper, is the ablation analysis. And here they are trying to, they're trying to understand what is it in the network that is contributing to this kind of performance. So what they try to do is that they don't use a conditional prior, but they fix the prior. In another case, they, in addition to fixing the prior, they also don't condition the posterior on the input, and also they try to inject the latent features at the beginning of the UNet instead of at the end. And in this case, their method as they presented it is performing the best on all the number of samples, including on one as well, comparing to the other variations of it. So, I mean, this graph, I think, just tells us that what they went with is gives us the best performance, but it still doesn't explain why they chose specific, why they chose the architecture to be this way. Why exactly they chose the conditioning on the input in such a way that they did. Why did they chose the latent space to be the distribution and axis aligned Gaussian instead of anything else, and so on and so forth. They don't, this does not explain us those choices, but it does give us a little bit of the understanding of why they might, but they tried different and then they saw that this one works the best. And so that is what they went with. But that's also a speculation of like, this was exactly the way they do it. Okay, in conclusions, well, we do have a model that provides the consistent segmentation masks that closely match the multimodal distributions. It is able to capture the complex output distributions, including very rare modes, also in the cases when there was no lesion at all. It outperformed the baselines on the 4, 8, and 16 sample cases by a significant but still thin margin. It disentangles prior net and the segmentation net, conditioning on the entire image while allowing for a better, for smaller computational costs, because it can be, the outputs of those can be reused to just generate as many images as required, and as many masks as required. And they also allow to inspect the latent space because of the VAE component. So they can look into, they actually have a whole section in the appendix on this. And then the experiment setup allows for in-depth performance evaluation. Here we are talking especially about the Cityscapes dataset, where they had artificially created the whole ambiguity and were able to have the full ground truth distribution and compute the performance on it. And they are claiming that this is something that others can be using when extending the future work, so that it's not only the visual, not only the visuals we are looking at, but also have very like full ground truth quantitative performance. A little bit on the criticism side would be, since they make the claim, one of the selling points of this method is that it provides the good model calibration, the well-calibrated model that is able to capture rare frequencies. And given that the performance on the metric has been better by a thin margin, and the method is a bit more complex, maybe they could add a little bit more to this, to support this claim. And then there was basically lack of the description behind the choice of the different architecture components, including why they condition on prior and posterior, why they condition the prior and posterior, why they are training these networks, and why there's the beta in the loss. They sometimes just make a reference to the original papers where they borrowed the idea from, but not adding any explanations themselves of why they specifically chose it here in this setup. And also in some of the other papers, the method is a bit more elaborate. And thank you for your attention. What are your thoughts on this paper? Do you agree with some of the criticism, or do you think that they did a good job?
Yeah, I would say it was quite a matter-of-fact sort of paper. I totally agree that they didn't explain really why they did certain things, and yeah, whether it really is that much better when it comes to specific applications. Well, it was still a cool paper.
That is a good one.
Yeah. Overall, I see in the most recent papers, I see that this is more and more common, right? Like, so instead of explaining a good thought process behind why you chose this architecture and why you think it works, it's more of a, well, let's stack more layers. So let's grab these two things and combine them and see what happens. I don't necessarily think that's a bad thing, but it definitely adds to what I see as one of the problems in machine learning, which is that we don't really understand why these models are working. We just know that they're working. So when something goes wrong, there's no way to fix it. But overall, a really nice paper. Thank you very much.
Yeah, thank you.
Are there any more questions before I stop the recording? Comments?
Hi. If I can have some comment. So I think the choice of that there was a question that why they choose and why in general VA chooses axis-aligned Gaussian distribution for prior. I think that's there are a couple of reasons. So whenever you train without a prior, you would see that different clusters, different classes of the objects that you want to learn became in very much separated space, and the space in between them usually gets very uncertain. A lot of samples can be generated from there that has nothing to do with the interpolation nature that we expect to happen. So if you have some distribution that simply just makes the samples to be compact and close enough to each other, so you're somehow regularizing the space in which the representation can happen, then it would probably help to infer the cluster boundaries in between different objects. Otherwise, there would be a wide range of possibilities to change from cluster to cluster, and eventually the network will generate very strange samples out of it. So the reason why they chose something for this is just the matter of simplicity, probably, that simply drags samples closer together. On the other hand, training axis-aligned Gaussian means also that that each of the variables became independent from each other. So basically, it's very simple to learn, even the simplest network can do that, and you don't hardwire it. Which is also a nice thing, that you don't hardwire it freehand. So I think that's kind of a good choice whenever you don't have enough samples. What is I think a kind of a question here is that for me is that they're measuring the ground truth to ground truth sample variance during the benchmark, and that's kind of a question whether it makes sense really. And on the other hand, what I'm usually most curious about on probabilistic models is that what can we learn from the generated confidence or probability? So naturally we would have the expectation that the variance would be larger for those samples for those inferences where our model is failing, so that we would have some sort of indication that something is going wrong because the model is uncertain about the prediction. And this is the confirmation that I'm always looking for in papers, and I rarely find, unfortunately. And if you see that this paper says that it is best performing all because it reliably reproduces results from experiment to experiment, which is okay, kind of a natural expectation from even from a sampling type of machine learning Bayesian model, but it's just not satisfactory for me. So I think we are still lacking the analysis of the results in that respect. So thank you.
Well, thanks very much. That was very detailed. Sure helped me. I can answer the first question you asked about whether it makes sense to compare the difference between ground truths. This is something that is frequently done in the medical domain, precisely because there's differences in the ground truths. So I had never seen it aggregated like this. Normally they would say that they would say like they would compare performance of the model to each of the annotators, and then they would compare the performance of the annotators versus the other annotators as well. So they show that the model is actually closer to the others, and so on.
Yeah.
Okay. Okay, so we've run out of time, so I guess that's a good thing, because it was a very interesting discussion. Thank you to everyone who participated. If you have a second to just fill in the poll, there's a question there at the end if you would like to change topic for next week. I guess most of you do want it, so we'll try to find a new topic. Thank you, Christina, very much. It was a really interesting presentation. Can we give a show of hands to show our appreciation?
Yeah, very much.
Thank you very much.
Thank you.
And yeah, so that's it for today, but we'll see you in the next session of Paper Club. Thanks very much.
Thank you, bye.